Okay, in the last class, we plotted together a Simulink, and I did with you that we had closed the transfer function of a marginal stable system like a pendulum. We found G here, 1 over S squared, open the transfer function, put an unity feedback block diagram, and I taught you how to generate impulse from the step by differentiating in frequency means S. And also I did a delay and to show you what's the effect of delay. And even I showed you if you put the delay, if you have a controller actuator here, what's the effect of that? Then I showed the step. Then I showed you the ramp. But I don't know why mistakenly I have to correct this. For the parabolic, we changed the transfer function from the previous class. You remember it, right? But I don't know why I put this here because ramp is 1 over S squared Laplace. So in 1 over S, 1 over S cubed, which is transfer function of what? Parabolic. So I have to put it here, guys. I don't know why I did it here. Okay, maybe I was tired. So I'm going to share the modified Simulink with you. Now you're going to put this here, okay? Then now this is parabolic. See, I'm writing here because I'm going to share with you here. Multiplying ramp by 1 over S gives you parabolic. Okay, 1 over S cubed. So if you run that, just you have a slight change here. Okay, here we go. Here we go. This is parabolic input. The output is sine. You can just do this. I'm sorry, like here. See, this is sine. So they have increasing what? Error signal. Increasing error signal between them. Okay? So it was just a misplacement of 1 over S. I just want to tell you this, okay? I'm gonna share it again, okay? And let me rename this because I'm gonna forget when I'm sharing with you. ME530, I'm gonna say modified, okay? Modified when I'm sharing it. Okay, so I'm gonna close it for now. Okay. Now let's go to first order systems. So okay. First order systems. For this class and the next class, I'm going to show you that R and capacitor voltage, input voltage from high voltage to low voltage. This is resistor from high school physics. This is capacitor. Dynamically, this is equals to the guys that you had vibration with me in the previous semester, ME520, what I'm going to teach you. This is equal to spring and damper in parallel, and you have a force. This can be regarded as your car suspension system, spring and damper. K, stiffness of the linear spring, and damping coefficient, C. And this is equal to, they are the same system dynamically, control-wise. I'm going to drive it for you. A tank of water. A tank of water. So you have inlet flow here. Please mute your speaker, guys. Please mute your speaker. please. Q in and Q out. Inlet flow, flow rate, outlet. So you have a height here, height of the fluid, whatever it is. I say here's water. H. And you have a valve here, valve, like as your kitchen sink valve. I say R of tank. Valve is resistance, like as this resistance. And your tank has a capacity, like as 2 gallon, 3 gallon. I'm saying CT, like as this capacitance here, C. These are dynamically the same system. And this is your art as engineer to understand this. And if I tell you all of these has this closed loop transfer function. Output over input is over 1 over tau s plus 1. All of this I'm going to show you today and by simulating the next class. That's why I say first order system. S to the power of 1. First order system. Clear, everybody? Yes? You got it? Huh? So this system, first order systems, I'm speaking generally. RC circuit, we say RC circuit, or spring and damper, or tank of the water, they have 1 poles. First, because this is this is from kindergarten. Poles is 1 minus over tau. This is equal to 0, 1 pole. And this pole is located at, in the complex plane, stop me where it's too much, imaginary real axis. Here is 1, we are showing pole by cross. Okay, this is convention. Here is 1 over tau. And you see the pole is in the left hand side. I taught you previously. When the pole's on the left hand side means your system is stable or unstable? Stable. If the poles are the right hand side, I taught you, means unstable. If the poles is on the imaginary axis, means your system is, tell me, I taught you a million times, means what? Like a pendulum. You tell me. Yes, marginally stable. Everyone got it? So the first order system you see here that they are dynamically equal has 1 pole in the left hand side, so it means that it's stable. What I'm going to do, I'm going to apply impulse as I promised you after driving and showing it all of them like this. Unit step, ramp, parabolic input in the Simulink, and in math at first, then Simulink. And finally, I'm going to apply a harmonic input sine omega t for the first time. To teach you frequency response is technical name. The guys that they had what vibration with me in chapter 5, we had this topic, but in vibration, this is control. Frequency response. To teach you body plot in control for the first time. Body plot in math and in Simulink. Body plot. Okay, let's do that. Oh, can I go? Everyone? Yes? Okay. So, for the RC circuit that we were talking about, I'm just again plotting here. We in RC. From high school, you know that input voltage is equal to voltage of the resistor plus voltage of the capacitor, voltage across the resistor, VR, and voltage across the capacitor, VC. And from kindergarten, you know that VR is equal to Ohm law, RI, the current circulating inside the circuit. And you know that VC is equal to 1 over C integration of I dt. But what I want to find here, this is control. I want to find VC, voltage of capacitor, over Vn, closed transfer function of output. My output is the voltage of capacitor over input voltage. Closed transfer function. It's very easy. I'm gonna take this here. I'm gonna say Vn equals to VR is Ri. I'm writing here Ri plus Vc. Inverse of this from high school is this. I equals to C dVc over dt. I bet you have seen this in physics for capacitor. If you didn't see, it's very simple like that, just inverse. Inverse of the integral is derivative. I moved C here and then I integrated both sides. What I'm gonna do, simple like this. I'm gonna replace this I here. So you're gonna have Vn is equal to Rc dVc over dt plus Vc. By this assumption that the capacitor voltage at time 0 is 0. You know that when you turn on the circuit, voltage of capacitor is 0. It takes time that the voltage of capacitor reaches to the input voltage. You have to pass this electric circuit 1 in EC department. Right? So now what I'm going to do, I'm going to go to frequency domain. How? You tell me. How? To frequency domain, this is time domain, T. How? Laplace. So you're going to have V in S. I told you, Laplace of time derivative, df over dt is S. F of S minus F at 0, initial condition. So this is 0 because of this. Here we go. RCS VCS plus VCS. We got that. Closed loop transfer function of first order system RC. So VC, I'm dropping these S's because we know that, is RCS plus 1 equals to Vn. So, for God's sake, we have closed loop transfer Vc over Vn equals to 1 over RCS plus 1. But in the page when I promised you this, tau s, here we go. So this is equal to 1 over tau s plus 1. Tau has a technical name in control. The name is time constant. Time constant. Time constant has a definition. The time required your output reaches 63% of your input. This is technical definition, Vn. Time constant. I'm going to show you by Simulink, by math. So we showed that for the RC circuit, This is valid. First order system, which is stable because you have one pole in the left hand side. Here we go. Can I go ahead? Guys? May I? Good. Let me show that these two now equal, as I promised you. Spring and damper. 2. The guys that you passed vibration with me in FEMI 520, you are easy on that. Spring, damper. Here we go. And you have a force. K and C. When you're applying a force, you have a displacement here. X. So what I'm going to find output displacement over force. Close the transfer function of this. You know that you cut from the system from here, free body diagram, dynamics and vibration course, or ME 220. Here is going to be resistance force from linear spring Kx, resistance force from the damper here. Cx dot, linear damper. Reaction force is Cx dot. Velocity, x dot. Now let's take it back to ME 220. Let's call Mr. Newton. Sum of the forces in x direction is mx double dot. How much is mx double dot here, guys? Look at the figure. There is no magic, nothing. How much is mx double dot? How much is that? Come on. How much is mx double dot? Mass in acceleration. Look at this figure. How much is that? Do you see any mass here? Okay, good. 0. Here we go. Now here is positive, this side. Here is negative. So you're going to have F minus Cx dot minus Kx. Simple like that. This is positive side to negative side. Clear, everybody? Yes? So you get F equal to Cx dot plus Kx. This is time domain. How do I transfer to frequency domain? You tell me. Laplace. Guys, can you please mute your, because, so assuming that the x at time 0 is 0. Okay, assuming condition is 0. So you get at k x of s plus cs x of s is equal to f of s, or x of s, you're going to have k plus cs f of s. Or we got that closed loop transfer function x over f equal to 1 over k plus cs. Now what I'm going to do, for God's sake, I'm going to just factor out from this. I'm going to say c over k s plus 1. Right? See what I'm saying? Can I do that? So you have 1k here, like that. Everyone agree? Yes? So you can write x over f is 1 over k divided by c over s, c over k s plus 1. Now this is like that, exactly as we promised. Tau s plus 1. Here your tau is this. This is your tau. Damping coefficient over stiffness of the spring. This is damping coefficient. First order system, one stable pole. So, being said, you see that RC circuit dynamically is the case spring and damper. Bingo. Now let's say these two also the same. Tank out the water. Can I go ahead? Yes? Okay. 3. So, tank of the water. You see, I'm playing with the physics of high school still, except the Laplace of the university. Nothing changes. Outlet flow rate, inlet flow rate. The height of flow is h. We have capacity of the tank. C is for capacity. Capacity. And this contraction can be modeled as resistor, because your sink valve is contraction, that's right. Resistor of the tank, RT. This is for resistor. Okay, how to derive this? I want to see the closed loop transfer function of Q out over Q in, outlet flow rate, or over inlet closed loop transfer function. Guys, if you want to explain in RC circuit we have voltage, well, how are you going to explain to a 5 years old brother or sister or kid? By showing, not by mathematics. What is voltage? You are mechanical engineering students. If you cannot explain it, you are nothing. Show it to your brother, to your sister, to your kids at home without electricity. What are you going to do? You're going to pick up a ball and release it. What happens to the ball? What happens to the ball, guys? This is ground. This is the ball. You pick up a ball and you release from here. This height. What happens to the ball? It goes from here to here, that's right? Everybody? So voltage is h here, height. That's why we put like this, from high potential to low potential, from this height to this zero, plus to zero. In analogy, voltage is height of the flow in the tank. So the resistor of the RC circuit, we have RT, tank of the valve resistor. Capacity in capacitor is the capacity of the tank, CT. When you're going in shopping in the Ralph and you're buying a 1 liter of the water, it's the capacity, CT. Okay? You are dealing every day with engineering what you don't know. That's a problem. Okay. So from Ohm law, we know that the V is equal to Ri. Okay? So from here, you know that I equals to V over R. And also you know that I, as I showed you in the previous page, is C dV over dt. Okay. You understand? What is analogy of the I in the tank of the water? Current. We know that this is H, we just found it. This is RT, tank resistor of the valve. What is I? Just look at the figure. What is affecting the change of the H? Look at the figure. What is affecting change of the H? You tell me. You tell me. Hmm? Look at here, between RT. Exactly, flow. Exactly. Which flow? Q in or Q out? You have RT here. This is tank. Okay. What is affecting that? I wanted that you find the answer. Q in. That's right. Q in is equal to H over RT. We just found from the Ohm law. Let's see if it's correct. Bear with me. Here we go. Again. Tank of CT, DH again. Voltage is H. DT. What gonna affect on change of H with the capacitor? Q in or Q out? Gonna be Q in minus Q out. Net flow rate. Gonna change. D means change. D means change. You got it? Everybody? Yes? So what? Yes, everybody? You got it? Q in minus Q out. So what I'm gonna do, I'm gonna find Q in from here. Sorry, I'm gonna find H from here and put it here. And put it here. H gonna be RT Q in. So Q in minus Q out gonna be CT, tank capacitor, RT, DQ in over DT. You got it, everyone? Actually, it must be Q out minus Q in. Sorry guys, it's Q out minus Q in. The net flow. Okay, so if you move to other side, you're gonna have Q in plus CT RT DQ in over DT is Q out. This is time domain. How to transfer to frequency domain? Laplace. So you have Q in CT RTS because of the first time derivative plus 1 is equal to Q out. So Q out over Q in is 1 over CT RTS plus 1. So what's time constant of this? Here we go. This is tau. This is tau. Gonna be 1 over tau s plus 1. Bingo! You saw the tank of water. It calls to massive spring. I'm sorry, spring and damper, and it calls to RC circuit. They are three of them are first order system. with a stable pole in the right hand side with the time constant specified for each system. You got it? Yes? Don't forget, why is put Q in here? Because Q in RT is affected by only Q in, not by Q out. RT. Only affected by Q in, not by Q out. But here, when you're talking about change of height gonna be because of Q in and Q out. The net flow rate, Q out minus Q in. You got it? Yes? Everybody? So, can I go to next page? We saw that RC circuit, spring damper, and tank of water, all they have, I'm writing generally, like as I did for Simulink, closed loop transfer function of tau is plus 1. I don't care what is tau anymore. I'm talking now generally about first order system that you have one stable point at the left hand side. At the left hand side. When you go to, I don't know, electric circuit lab, or when you go to industry, when you look at the RC, you have to remind yourself, oh, this is tank of water. When you look at your suspension system of your car without mass, you go, oh, this is tank of water. Okay? This is art of engineering. Okay? To make analogy. 1 over tau. Now, as I promised you, I'm going to first apply x of t is impulse. So x of s, now you know it is 1. From here, the output gonna be 1 over tau s plus 1. Simple. But I'm gonna play with this a little. I'm gonna say I can write as this 1 over tau s plus 1 over tau. I can rewrite like this. Now I'm gonna find solution back in time. What I have to do, I taught you, solution in time, Laplace inverse. So y of t, for any of this system I taught you, not only for tank of water, for all of them, this is 1 over tau. Which function gives you such a transfer function? Laplace of e minus at, you have your notes, is 1 over s plus a. I taught you, you have your notes. Your a is this. So it's going to be 1 over tau, e minus t over tau. Bingo. For first order system. Now, if t is 0, simple like that, your y of t gonna be 1 over tau. Because this is 1 over tau. If t is 1, your y of t gonna be, can you please use calculator and let me know how much is this? 1 over tau e minus, I'm sorry, if t is tau, I'm sorry, gonna be minus 1. Can you tell me how much is this? I know the answer. I wanted that you do it. Can you please do that? E to the power of minus 1. Anyone? 0.36. I don't care about the rest. Okay. 1 over tau. I'm working on this number. If t is a large number, say infinity, your y of t gonna be 0 because this is 0. Gonna be 0. Let me plot it for you guys. For any first order system with a stable pole, at time 0 is 1 over tau here. At tau, We define tau as what? You tell me. We define tau as what? Time constant. It is 0.36. Now let us look at the definition of the tau. Time required your output reaches 63 of your input. 63 plus 36 gonna be 100%. So here we go. Here we go. This is 0.36. Here we go. Here you are at tau. We reached to find it, and it goes to 0. There we go. What was the input to the system? Impulse. You see that at tau it reaches 63 of 0. Here we go. You understand what I have done? Yes, everybody? Yes? 36 plus 63 is 100. At t is equal to tau, okay? Oh, where's here? Here. Oh, this is so badly plotted. I'm sorry. Here we go. This is your tau. And this is your input. Impulse. At here you came down how much? How much is here? 63%. And the remaining is 36. You got it, everyone? So now let me do 2. I say the input to the system is a step, means 1 over s. So y gonna be 1 over s in tau s plus 1. You can decompose as a over s from high school plus b over tau s plus 1. Okay? You got it? So the trivial version is that you're gonna say this is a tau s plus 1 plus bs in s tau s plus 1. This is equal to how much? Equal to 1. Just the number the same. This is very trivial, okay? I'm sticking to that. So you're gonna have a tau plus b in s. I'm writing plus a is equal to 1. This one. There is no s here, so you're gonna have a tau plus b is 0. A is equal to 1. Here we go. If you implement this here, you get b is equal to minus tau. So y gonna be 1 over s minus tau s plus 1. You can write as I did before, 1 over s plus 1 over tau. Let's get back to time domain. What I have to do, guys, again, I'm just repeating myself. Laplace inverse. Which function gives you this in Laplace? Which function? You tell me. Which function? Unit step, the input. So y of t gonna be unit step minus, we did that in the previous page, e minus t over tau. Bingo. I taught you, what's the name of this in mathematics? What's the name of this? I taught you, you have in your notes. Decaying term. It vanishes. Remember? You have in your notes. Means that when time goes to a large number, this goes to 0 this term. And eventually y of t equals to this. And I'm gonna plot it for you. For any first order system, tank of water, RC circuit, spring and damper with stable pole on the left hand side. This is the input to the system. Unity step 1. And the output based on this gonna be, let me plot this. It says finally output follows the input, goes to 1. Here we go. When the output follows the input finally, what is 0? You tell me, I taught you in the block diagram. What is 0? What is 0? Error signal is 0. You got it? Everyone? Yes? Can I go to next page? So, before going to the ramp, I taught you that open loop transfer function is 1 over tau s plus 1. Now I want to plot in the Simulink, in the unity feedback system X. What do you have to put here? You tell me. What do you have to put here? Closed loop or open loop transfer function? Which of that? I taught you 10 times. What do you have to put here? Open loop. So you have to find it from here. Open loop for unity feedback is G1 plus G. I'm skipping the math. Please do at home. G gonna be 1 over tau s. So here you have to put, even in Simulink, 1 over tau s. When I was talking about the error signal, I said the output follows the input. This is output. This is input. Means output follows input. So error signal gonna be 0. I'm gonna show it to you. Again, here we have to put in unity feedback. You have to put open loop transfer function, not this. Not this. Unity feedback. Let me do also this one. I'm gonna do the rest next class, and next class I'm gonna do Simulink. 3. If the input to the system is ramp, means 1 over s squared. So y gonna be 1 over s squared s plus. Sorry guys. Come on, please. Okay. I think I have to open. Let me do that here. Y gonna be 1 over s squared tau s plus 1. You know how to write it from high school because you have 2 repeated 0 here. Go to s squared plus b over s plus c over tau s plus 1. You know, you can write as this: a in s in tau s plus 1 plus b s squared tau s plus 1 plus c s squared. Because this is s squared tau s plus 1. Sorry guys, this must be, oh, I cannot delete this. This is a multiplied by that. Guys, please delete this a, this s from here. We don't have this s here. We don't have this s. And here we have one s. Let me write it here because I cannot fix it now. It's gonna be a tau s plus 1 plus bs tau s plus 1 plus cs squared. The same here. Same. If you write like this, resort that, you're gonna have C plus B tau in S square plus B plus A tau in S plus A equals to 1. From here you get A is 1. From here you put here, because this is 0, B gonna be minus tau. If you implement here, you get C is equal to tau squared. Bingo. Okay. I have to open a new PowerPoint. Okay, so y gonna be 1 over S squared. What was the B? Minus tau, that's right. Over S plus C is tau squared. Tau S plus 1. Before applying Laplace transform, we're gonna have this minus tau S plus tau S plus 1 over tau. I reshaped this. Now let's go back to the time domain. Laplace inverse. You know that this is ramp, input to the system. So y of t is t ramp. This is unit step minus tau unit step. And you know this, what is this? I taught you, is tau e minus t over tau. I already taught you today. What is the name of this? You tell me again. What is the name of this? I just taught you. Means goes to 0 when time goes to infinity. This is high school. Guys, this was output. What was this in this case? Tell me. Ramp was what? Look at here. Oh. What was what? Input, ramp, that's right. Everybody? You got it? How to call them now? Oh my God. There we go. So T was input to the system, remember? Input. Now look at here, guys. Going back to unity feedback control. X 1 over tau S. Open loop transfer function Y. What is input minus output? What was the name of signal here? You tell me. Error signal. See what I'm saying? So T minus Y of T, input minus output, is error signal, E of T, error signal. It is how much? Constant number, tau, because this is 1. Tau means that you have, technically speaking, this is technical name I'm teaching you. You have steady state, not vanishing. Steady state error signal. Error signal equals tau. For RC circuit is RC. For tank of water is R tank, C tank. For spring damper was C over K. So as it promises, if I plot this, y over t. This is the input to system, ramp. Oh, sorry, I'll change the color. This is ramp input to system. And output is this. Here we go. Here is a constant error signal. Here is tau, here is tau, here is tau, here is tau. This is error signal, E, 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 E. You see what I'm saying? See that? Following me, everybody? Good. So I'm going to stop it here. I'm going to do the parabolic next week. I'm going to go to Simulink and we're going to move to second order systems. Okay? Everything is pretty straightforward. I'm just repeating myself. If you stick to the fundamentals, I'm repeating myself. Okay? So, bear with me.